Ever found yourself just sprinting through a major airport? Like, let's say you're making a really tight connection at a massive hub, maybe Atlanta or Heathrow.
Oh, yeah. The absolute worst.
Right. And you feel like the actual layout of the building is just actively working against you. You know the exact feeling I'm talking about. You're rushing to your gate, the signs are pointing you down this corridor, and then suddenly you just hit a completely inexplicable wall of people.
Just a total bottleneck.
Exactly. It's like there's a massive jammed up elevator bank or this confusing hallway that seems to squeeze everyone into a literal funnel while, the giant lobby sitting just 20 feet to your left is completely empty.
Yeah. It's a universally frustrating experience. And I mean, we usually tend to blame ourselves in those moments, right? Thinking like, oh, I just took a wrong turn or I'm traveling at a bad time.
Oh, for sure. I always think it's my fault.
But honestly, more often than not, it is a structural failure of the spatial design itself. The building was designed for structural integrity, and aesthetics, but it just simply wasn't prepared for the mechanics of how actual humans behave in reality.
And that is exactly what our mission is for today's deep dive.
Yeah.
We are looking at a really fascinating document from Roots BIM LLC. And it centers around this concept called Human-Centric BIM.
Right.
And just for those unfamiliar, BIM stands for Building Information Modeling. But what this document lays out is a massive shift that is currently happening in the architecture and construction industry right now. They're moving away from designing buildings around pure static geometry, and instead they are designing them around us, like around actual human behavior.
Which, I mean, that represents a profound philosophical shift in architecture because for the longest time, a modern building was judged primarily by two things: how it looked from the outside and its structural complexity.
Did it look cool and did it stand up?
Exactly. Did the glass facade look impressive against the skyline? Did the developers manage to build it under budget? But this source argues that the true performance of a facility today shouldn't be judged by the shell, but by how effectively people interact with the space inside it.
Okay, let's unpack this. Because to really appreciate how we're fixing these frustrating buildings, we first have to understand how they've historically been designed. And frankly, where that old process fell short.
Yeah, so to understand the shortfall, we have to look at traditional BIM workflows. Historically, architects and engineers have used these digital models, and they were incredibly useful, but they were entirely focused on static, physical elements.
Just physical stuff.
Right, we're talking about geometry coordination. They use this process called clash detection, which is essentially running a computer program to make sure a plumbing pipe doesn't accidentally intersect with a load-bearing steel beam in the digital model.
Before they actually start pouring the concrete.
Exactly. It was strictly about scheduling, physical documentation, and cost management.
So it's basically making sure the physical puzzle pieces fit together so the building doesn't collapse and, doesn't bankrupt the developer in the process.
That is the core of it, yeah. But what traditional BIM completely ignored was the human element. It just didn't account for how an actual living, breathing person would move through those beautifully coordinated geometric spaces.
It really reminds me of like a team of engineers building a beautifully complex, incredibly expensive car engine. They obsess over the pistons and the fuel efficiency, but they entirely forget to measure if a human driver can comfortably reach the gas pedal.
Right, right.
Or like if the steering wheel blocks their view out the windshield, you end up with this mechanical masterpiece that is completely useless and potentially dangerous to the person who actually needs to operate it.
That is a brilliant way to frame the problem. And it really explains why the shift to human-centric BIM is so critical right now. What's fascinating here is that the source material outlines how designers are now integrating factors like occupancy behavior, movement dynamics, cognitive comfort, and spatial efficiency right into those core digital models.
But how are they actually getting this data? Because, you can't just guess how 3,000 people are going to feel in a convention center lobby. Human behavior is notoriously unpredictable.
Oh, they aren't relying on guesswork or intuition anymore. Not at all. The document details the heavy use of behavioral data analytics. So they are gathering massive anonymized data sets from the real world using IoT sensors.
Internet of Things.
Exactly. So think about the infrastructure that's already in our buildings right now. They use Wi-Fi access point tracking to see how devices move through a space.
Wow, okay.
Yeah, they use badge access control systems to see when people enter and leave zones. They use smart cameras with computer vision and even environmental monitors that measure CO2 levels to detect how many people are breathing in a specific room.
Wait, CO2 levels? That's wild.
It is wild. They take all this data about how people physically interact with built environments and feed it directly back into the BIM software.
So what's fascinating here is that we are talking about transforming BIM models from these static, lifeless digital blueprints into what the source explicitly calls predictive behavioral ecosystems. The model ceases to be just a drawing and becomes a simulation that is just alive with data.
Yeah, it fundamentally changes the definition of a blueprint. It's no longer just a 3D rendering of a 50-foot hallway. It's this digital environment that mathematically knows that at, say, 8:45 a.m., 300 people are going to try to walk down that 50-foot hallway at the exact same time.
Carrying coffee and looking at their phones.
Exactly. Carrying coffee, looking down at their phones, and trying to scan a badge at the elevator bank.
Okay, so preventing a stampede in a hallway is an extreme use case, but it leads perfectly into my next question. If the building is now treated as a predictive ecosystem, how do designers actually simulate that chaos before a single brick is even laid? Like, how do they predict what a crowd will do?
Well, that brings us to one of the most powerful technical applications mentioned in the Roots BIM document, which is crowd flow simulation. This is where the engineering gets incredibly sophisticated.
Okay.
They start by combining the standard architectural geometry. So you might hear terms like Revit or IFC files or Navisworks coordination data.
Right, the industry software stuff.
Yeah, simply put, these are the software programs that create the digital skeleton and the nervous system of the building. The walls, the floors, the wiring. They take that digital skeleton and they drop advanced AI-driven algorithms inside it.
So they build the digital terrarium, and then they just drop the AI in to see what happens.
Yes, exactly. Through a mechanism called agent-based modeling, or ABM. In these simulations, every single occupant isn't just some mindless dot moving along a pre-programmed track. Every person is treated as an independent agent with unique characteristics.
I love this concept. The document says these agents have their own movement goals, their own decision logic, speed variability, and even spatial awareness. So I'm trying to visualize this. Is this essentially like playing the video game The Sims, but using hyper-advanced AI to simulate a stadium rush hour or an emergency evacuation?
Honestly, the Sims comparison is highly accurate for understanding the mechanics. In that game, your characters make choices based on their internal needs and their immediate environment.
Yeah, exactly.
In agent-based modeling for commercial building design, these digital agents are programmed with really complex behavioral logic. For instance, they have speed variability. A 20-year-old agent might walk at a faster pace than an 80-year-old agent.
Makes sense.
They also have what you might call a patience threshold. So if an agent sees a massive line for an escalator, their programmed logic might dictate that they just turn around and search for a set of stairs instead.
Which introduces an incredible level of realism, but it also makes me think about the darker scenarios. You mentioned emergency evacuations earlier. The text specifically calls out simulating panic reactions.
Yeah, it's a sobering thought, but it is absolutely vital for life safety engineering. By simulating emergency panic behavior, designers can see exactly where a dangerous crush of bodies will form if, say, a fire alarm goes off in a crowded nightclub or a high-rise tower.
Right.
And to figure this out, the AI uses advanced pathfinding logic. The document mentions A-star algorithms and navigation meshes.
Okay, I want to pause you right there because A-star algorithms and navigation meshes sounds like really deep computer science jargon. Can we translate that into how the agent actually finds the exit?
Oh, for sure. Let's
Yeah.
break it down. You can think of an A-star algorithm, much like the GPS app on your phone. When you hit a traffic jam on the highway, your GPS instantly recalculates the path of least resistance to your destination, right? The agents in the simulation do the exact same thing in real time. If an exit is blocked by smoke or a crowd, the A-star algorithm calculates a new route, and it factors in not just the physical distance, but the density of the human traffic in front of them.
And a navigation mesh.
The navigation mesh is basically like an invisible grid laid over the floor plan that tells the AI where it can and cannot step. It defines the walkable terrain. So it knows it can't walk through a solid desk, but it can squeeze between two chairs.
Ah, got it.
Yeah, so by combining these tools, designers can optimize fire exits, they can test the capacity of the stairwells, and plan out refuge zones. They even simulate smoke movement interactions. If the model shows smoke filling a primary corridor, they can watch how the digital crowd reacts to that sudden rerouting, just ensuring the secondary exits don't immediately become fatal bottlenecks.
So before they even pour the concrete for a transit hub, they have already watched thousands of AI agents try to evacuate it under the worst possible conditions.
Exactly.
That is just preventative spatial engineering. You are fixing the traffic jam before the road is even built. But let's shift gears a bit. Surviving an emergency or navigating a dense crowd is step one. What about a normal Tuesday in the office? How does this technology apply to actually using the spaces once we get to our destination?
Well, this brings us to a concept the document calls space usability prediction. This really transitions us away from crowd survival and into everyday cognitive comfort. For decades, space planning in corporate environments relied on generic area calculations and historical standards.
It's just standard math.
Right. A company moving into a new headquarters would just estimate based on a spreadsheet. They'd say, well, we have 100 employees, so standard math says we need 100 desks, a break room, and 3 conference rooms.
Which usually results in 50 empty desks because half the team works from home on Fridays, and everyone is throwing elbows over the one conference room that actually has good lighting.
You are hitting on the exact problem of the modern workplace right there. Behavioral BIM completely abandons those generic assumptions. It uses a very specific 4-step technical workflow to predict and optimize how spaces will actually be utilized.
Okay, walk me through the steps.
So step 1 is BIM model development. This isn't just drawing the room. This is where architects add spatial metadata and functional zoning to the model.
Meaning they are tagging a specific square of the digital floor plan and explicitly defining, like, this is supposed to be a high-focus quiet zone, or this is a loud, collaborative brainstorming area.
Precisely. Once they define the intent of the space, they move to step 2, which is behavioral data integration. This is where they layer in the real-world data we talked about earlier. They stream in the badge access logs, the IoT occupancy sensor data, and the mobile analytics from similar existing buildings.
Okay, so now the model has the physical layout, its intended purpose, and just a flood of historical human data. What is step 3?
Step 3 is analytics and machine learning. The AI churns through all that data to evaluate utilization frequency. It looks at how long people actually stay in a room and measures human interaction density.
Right.
And that leads directly into step 4, which is predictive optimization. The system actively flags underperforming spaces, overcrowded areas, poor furniture placement, and even HVAC load mismatches, all before the design is finalized.
Hold on. Here's where it gets really interesting, though, and I need to push back on this a little bit on behalf of anyone listening who works in a corporate office.
Sure.
Because the idea of behavioral data integration sounds incredibly invasive when you frame it that way. Does this mean the modern hybrid workplace is constantly monitoring our individual badge logs and tracking our precise movement just to adjust the lighting and the air conditioning? Like, if I walk into a shared collaboration zone tomorrow, is the building actively analyzing my presence to figure out if my desk is inefficient? It feels a bit like Big Brother. How are they actually separating my personal identity from my digital footprint in this model?
It is a highly valid concern, and honestly, one the industry takes very seriously. But let's look at the mechanics of how this data is actually processed. The goal outlined in the text isn't about tracking you as an individual named employee. It is about tracking aggregate behavior to reduce wasted floor area and improve environmental response.
Okay.
In most advanced systems, the data is anonymized at the edge, meaning the sensor detects a heat signature or a moving mass, not a specific ID badge.
So it knows a warm body is sitting in a chair, but it doesn't care that the warm body is me.
Exactly. Let's look at a micro scenario to make it clearer. Imagine a large conference room that the company spent $50,000 outfitting. But the AI sensors detect that for the past 6 months, people only ever occupy the chairs on the left side of the table. The right side is a complete dead zone.
Oh, interesting.
The system flags this as a spatial failure. When the designers investigate, they realize the window placement causes a blinding glare on the presentation screen for anyone sitting on the right side. The sensors didn't care who was avoiding the chairs. The aggregate data simply highlighted a flaw in the cognitive comfort of the room.
Wow.
So then the AI suggests rotating the table 90 degrees in the next floor plan iteration.
That makes a lot of sense, and it definitely lowers my blood pressure regarding the privacy aspect. It's about making the building work for the human collective, rather than forcing the humans to adapt to a rigid, poorly designed room.
And the downstream effect of that is massive for a company's bottom line. Think about a hybrid work model where occupancy fluctuates wildly from day to day. Heating and cooling empty sections of a massive office building is a tremendous waste of energy and capital.
Oh, sure.
By using this predictive data, organizations lower operational costs, they improve employee comfort, and they turn the office into a responsive digital ecosystem. It takes all the historical guesswork out of interior design and facility management.
And as the Roots BIM document details, this technology isn't just reshaping the corporate office. It is actively redesigning some of the most high-stress, high-stakes environments we interact with on a daily basis. Let's talk about healthcare, because the implications there seem incredibly profound.
Healthcare architecture is arguably where this technology has the absolute highest stakes. Think about the layout of a modern hospital complex. They are using human-centric BIM to optimize patient movement, but more crucially, they are using it for infection control circulation planning.
Wait, seriously. So they can actually simulate how air currents and human foot traffic overlap to minimize the spread of something like a virus through the corridors.
They absolutely do. They can map out a digital hospital and simulate the exact path an infectious patient might take from the triage desk to an isolation ward. The simulation tracks their movement speed, the air pressure zones they pass through, and their proximity to vulnerable patients in nearby waiting areas.
That is mind-blowing.
It really is. They use the AI to design physical barriers and adjust HVAC airflow to ensure cross-contamination risks are minimized. Furthermore, they simulate emergency medical responses to ensure a critical patient on a gurney can get from the ER doors to the operating room without hitting a spatial bottleneck.
That is incredible. And, the source material also highlights airports, which brings us right back to our opening scenario. The text specifically mentions managing passenger flow, security queue management, and boarding efficiency. So the next time I am actually moving quickly through a TSA line without feeling like cattle, I might have an AI simulation to thank for that layout.
You very well might. The AI agents we talked about earlier simulate thousands of different queue layouts to find the one that reduces anxiety and speeds up the security screening process.
Wow.
And it extends beyond transit, too. The document notes its use in retail and commercial spaces for consumer movement analytics and engagement heat mapping. They can predict where checkout congestion will occur. In massive stadiums and event spaces, they use it for crowd safety and exit strategy optimization.
Imagine they also use it to figure out exactly where to sell the beer and hot dogs.
I mean, it sounds trivial, but concession circulation management is a massive logistical hurdle in a stadium. The AI can predict exactly where the line for a popular food stand is going to bleed into the main concourse and completely block the pathway to the restrooms. They design the concourse width based on those predictive flow models.
It really touches every single aspect of our public lives. We don't even realize how heavily engineered our walking paths are. But there is one final concept in the source material that we really need to cover, and it represents the ultimate evolution of everything we've discussed today, the concept of digital twins.
Ah, yes. This is where all these disparate technologies, the BIM blueprints, the IoT sensors, the AI algorithms finally converge. A digital twin is exactly what it sounds like. It is a real-time, highly accurate digital replica of the physical building, continuously updated with live data.
Let me try out an analogy here. So a digital twin is basically a highly advanced voodoo doll of the building. Like, whatever happens to the real physical building in the real world, say a sudden temperature spike on the 4th floor or a massive unexpected crowd surging into the lobby, happens to the digital model on a computer screen in real time.
I mean, I have never heard it called a voodoo doll before, but yeah, structurally, that is exactly how the feedback loop operates. Because of this continuous flow of real-time occupancy intelligence, the building ceases to be a static, finished object the day the ribbon is cut. It becomes a living, breathing system.
So what does this all mean for the future of how we live and work in these spaces? The document states that the building evolves from a static structure into an intelligent, human-responsive system.
If we connect this to the bigger picture, it means the future of architecture is undergoing a radical redefinition. A building's success won't be measured by how tall it is or how complex its steel framework is. It'll be measured entirely by cognitive experience and behavioral efficiency. These digital twin buildings will continuously learn from the occupants inside them. They'll adapt dynamically to changing weather conditions or shifting work schedules, and they will predict behavioral trends to optimize their own energy use and spatial flow automatically.
I want to read a direct quote from the text because I think it perfectly encapsulates this shift. Quote, Because the next generation of buildings will not simply contain people, they will understand them, unquote. That is a powerful, almost slightly intimidating way to frame it.
It is powerful because it fundamentally changes our relationship with the built environment. We are used to adapting ourselves to the infrastructure. In the near future, the infrastructure becomes an active, empathetic participant in our daily routines.
It really does. So for you listening, the takeaway here is pretty incredible. The next time you effortlessly navigate a crowded international airport, or you manage to find a perfectly quiet, well-lit collaboration space in your hybrid office,
Hmm.
or you easily exit a stadium after a massive concert without feeling crushed in a stairwell, remember that it probably wasn't an accident. And you didn't just get lucky.
Definitely not.
An AI agent, with your approximate walking speed, your patience threshold, and your spatial awareness, likely simulated your exact experience thousands of times, years before the foundation of that building was ever poured. The space was quite literally designed around your predicted behavior.
It's a fascinating hidden layer of behavioral design that most of us will never consciously notice. And that is by design, precisely because when this technology works perfectly, the architecture feels completely invisible.
The absolute absence of friction is the ultimate proof that the design worked. But walking through all this does leave me with one final thought to mull over. It's something that isn't explicitly answered in the Roots BIM text, but after hearing how advanced these digital twins are, it feels like the natural next step.
What's that?
Well, if our buildings are becoming these intelligent performance ecosystems that constantly monitor and learn from our behavioral data to optimize their own efficiency, at what point does the building start subtly manipulating our behavior to make its systems run smoother?
Now, that is a truly fascinating, complex question.
Right. I mean, if the AI running the digital twin knows it needs to prevent a bottleneck at the main exit to maintain its own optimal efficiency score, could it subtly use ambient lighting, slight temperature drops, or dynamic digital signage to hurt us exactly where it wants us to go?
Wow.
Are we walking a certain path because we chose to, or because the building engineered our environment to make us choose it? It is definitely something to think about the next time you find yourself instinctively following a perfectly lit, gently curved hospital hallway. We will leave you with that. Keep questioning the spaces around you, keep exploring, and we will catch you on the next deep dive.